In this lab, we investigated the motion on an inclined plane and how the velocity changes over time. We also investigated how the object moving upward slows down due to gravity, and if it was to move downward, it speeds up due to the gravitational acceleration. Then we investigated also if the acceleration depends on the angle of the incline and not the object's mass, or the other way around. The materials used for this lab was a glider and an air track, a ruler, two weighting masses, and two extra weights to adjust the height, along with a sensor to calculate velocity. The formulas used for this lab were to calculate for sin theta, which is sin theta equals opposite over hypotenuse. Then our next formula used was the theoretical acceleration, which is calculated by a of acceleration equals g of gravity times sin of theta. Then our experimental acceleration, which is a of acceleration equals delta b, which is change in velocity, over change in time, which is calculated by graphing the final minus initial velocities over final minus initial times. Then we have our percent error formula, which is calculated by percent error equals theoretical acceleration minus our experimental acceleration over our theoretical acceleration again times 100. Then last but not least, our percent difference equation, which is percent difference equals our old value minus our new value over our old value times 100. Then for our lab analysis, we came to the conclusion that our opposite, which is our height, it was to be 3.1 centimeters. Our hypotenuse, it's 100 centimeters, which is equivalent of 1 meter. And our sin theta is what we're about to calculate. So to begin with, we use the formula of sin theta equals opposite over hypotenuse, which then we plug in our values, which is said to be 3.1 over 100. Then after we carry out our math, we get sin of theta equals 0.031, which is that our sin theta. Then to calculate our theoretical acceleration, we use the formula of A equals g times sin theta, which g is gravity. Then when we plug in our values, g it's equivalent of 9.8 and our sin theta was said to be 0.031. Then when we plug it into the calculator, we get a value of 0.303. Then we plug into our chart to not lose track of it. Then for our second table, after running the first experiment under low mass high tilt, we set our initial velocity to be 0.02 and our final one to be 0.99. Then we annotated our initial time and our final time, which is said to be our initial time is 0.05 seconds. Then our final time is 3.58 seconds. Then to calculate our experimental acceleration, we use the formula of A equals changing B over changing T, which we plug in as 0.99 minus 0.02 over 3.58 minus 0.05, which then if it's plugged into the calculator, we get a value of 0.275. Then we annotate it into our chart to not lose track of it. Now we're being asked to calculate the percent error, which is calculated by acceleration of the theoretical value minus acceleration of our experiment over acceleration of theoretical times 100, which our theoretical was said to be 0.303 minus our experimental, which it's what we calculated right now, 0.275 over theoretical again, 0.303 times 100, which then if it's plugged into the calculator, we get a value of 9.57% error. Now for this chart, we decided to run it with high mass and high tilt as it said. And after we run it, we said the initial velocity was to be 0.05. Our final velocity was to be 1. Then we also needed our initial time and our final time like last time, which then we annotated, and our initial was set to be 0.05 seconds and our final was set to be 3.5 seconds. Then we're being asked to calculate the acceleration again, which is experimental because we just changed mass, which is said to be A equals our final minus our initial velocities, which is 1 minus 0.05, and the same thing with time, which is 3.5 minus 0.05, which then if it's plugged into the calculator, we get a value of 0.275. And again, we annotated it in our chart. Then to calculate the percent error again, we use the same formula as last time, which is A theoretical minus A experimental over A theoretical times 100. Which then, if it's plugged in our values into the formula, is 0.303 minus our experimental, which is said to be 0.275 over our theoretical again, 0.303 times 100. Then, if it's plugged into the calculator, we get a percent error of 9.12%. Now for this chart, we had to change some stuff such as the height, which changes our sin theta completely. Then by changing it, we get an opposite height of 1.55 centimeters. Our hypotenuse stays the same under 100 centimeters. Then to calculate sin theta, we use the same formula of opposite over hypotenuse, which then if we plug in our values into the calculator, which is 1.55 over 100, it gives us a value of 0.0155. Then we annotate it into the chart to not lose track of it. Now to calculate our theoretical acceleration, it's the same formula as last time, which is A equals G times sin theta, which is 9.8 times our sin theta, which is said to be 0.0155. Then when we plug it in, we get the value of 0.1519. Then we annotate it to our chart. And last but not least, to calculate our percent differences of our theoretical values, we run it under our percent difference formula, which is percent difference equals old minus new values over old times 100, which then if we plug it in, our old value was said to be 0.303 minus our new value, which is 0.1519 over our old one, 0.303 times 100. Then if we plug it into the calculator, we get a percent difference of 49% difference, and we go ahead and annotate it once again into our chart. Then our last table, we run it under a low tilt with no mass, which our initial velocity was said to be negative 0.46. Our final velocity is 0.47, and we annotated our times again to the corresponding initial and final times, and our final was 20.35 seconds. Our initial is 13.5 seconds. Then to calculate the acceleration, we again run it under the change of b over change of t, which then if we plug in the values, it should look like 0.47 minus negative 0.46 over times, which is 35 seconds minus 13.5 seconds, which gives us a value of 0.135, which is our experimental value of acceleration 3. Now, to calculate the percent error, we use the same formula as before, which is A theoretical minus A experimental over A theoretical times 100. And we decided to plug in the values as just how we used to do it before, which is our theoretical 0.151 minus our experimental, which is 0.135 over 0.151 again times 100, which gives us a value of 10% error. Overall, the steeper the incline, the greater the acceleration will be. The changing in the mass did not significantly affect the acceleration, and the percent error measured the accuracy of our experiment. Our minor errors were caused by friction and measurement limits, and last but not least, our results confirm that acceleration depends on an angle and not the mass. The credits for this video was that Sileme Rivero conducted a voiceover and assisted in analysis, Danitza Canales edited the video and captured recordings as well as photos, Diego Padilla assisted with the experiment, photos, and recording, Angel Aguirre assisted with the experiment, photos, and recording, and last but not least, Annika Wagner helped conduct an analysis of data.